Okay, so hey everyone, a very good evening to all of you. This is basically the topic or the popularly known, terminology by which this domain of topics or domain of questions are taught and discussed. So, a very fresh topic, a very important topic for all your exercises. It is an important thing which one should know while you are targeting some competitive coding competitions, whether it is ICPC or simple contests like Code Forces and Code Chef. A very important and interesting technique. So we are going to look into this technique today. It would be nice if someone can confirm if you all can hear me clear, loud and clear. Then we will start into the topic. Okay, great. Thanks, Shanawaz. So we are going to continue now. So as we all know that DP is first of all, great. So DP first of all is a method of optimizing based on sub-problems that we have solved. We solve sub-problems and using the solutions we can solve our final problem. This is the core idea of DP. And bitmask DP is just a special category inside the variety inside DP which tells that the states are to be represented using bitmask. We will see what the cases are. We will see how basically that kind of a storage helps us. But first of all, it is important to understand a few things. Inside the domain of DP problems, what differs across DP problems is how they depend. So you have seen, suppose you have, LIS kind of problems. In LIS kind of problems, you have seen how they depend. It depends on all the previous values. In some cases, you have found a table kind of a structure where you have said that every row, whenever we are computing a single row, it depends only on the previous row's values. So there are various types of dependency. And we briefly say that there are basically two types of dependency in DP plus or in DP, the domain of DP. One is partial dependency, another is complete dependency. In case of bitmasks, DP plus bitmasks, what we basically deal with is a kind of complete dependency. So we deal with complete dependencies. In a way saying that as we proceed, you will see that our current answer will use the answers of many previous subproblems to compute itself. And this bit masking in a way also gives us the notion of exponential possibilities. Notion of exponential possibilities. We will explore this through a problem. But first of all, the idea of bits is necessary. So whenever we express a number, suppose I think 37, we can say 37 means it is 32 plus 5. So we can express this as 32, 16, 8, 4, 2 and 1. This is the representation of 37 in bitwise form. And what this indicates is that how the powers of 2 are present. This is the only prerequisite that when I mention the binary notation of a number, you are clear about what exactly it means. It means that these are the powers which explicitly define this. 2 to the power 0, 2 to the power 2, and then here you go 2 to the power 5. You have 2 to the power 5. These are the powers of 2 which actually define it. And in DP plus bitmask, we do a very different thing. We say that this 37, it uniquely determines that this is a congregation, or this is formed by the congregation of three different things. One is 2 to the power 0, another is 2 to the power 2, another is 2 to the power 5. Using these three things and maybe some other things, we can form many other things. Like if we just use 2 to the power 0 and 2 to the power 5, we are going to get a different number. We are going to get 33. So maybe like we can say that these are some elements, and based on the choice of these elements we are getting different outcomes. One such outcome is 37, another such outcome is 33. And it is these elements that we'll be focusing on. So this is maybe one kind of a property, this is maybe another kind of a property, and this is another kind of property. If those three are present together, then in a way I can say that it represents the presence of 37. This is how we visualize a bit mask. When we see a bit mask, or when we see the mask formed by these various binary components, what we eventually get is the summation of them, and this sum tells me that these three things denote it uniquely. When these three things are present, I get this outcome. So I can say that if these three properties are present, I can represent it simply using 37. If only two of them are present, namely 2 to the power 0 and 2 to the power 5, which is P0 and P3, P1 and P3, don't worry about what exactly is P1, P2 and P3, we are going to see that. But the important thing is that they are being visualized as different elements. Every power of 2 is a different element to us. And when we want to take all possible subsets, we will basically see that the summations of these elements form a different outcome to us. So the outcome is sufficient to say what subset we are saying, what subset we are mentioning. I'll make it clear, a bit clear. You all can say if it is clear this much, but I'll make it a bit clear if it has gone hazy. Suppose you have got these values, 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3 and 2 to the power 4. We can say if you take all the values, we are going to get 31. This is by taking all the values. So 31 tells me that all the properties are present. All the properties are present. However, if we say we just want 2 to the power 1 and 2 to the power 3 and 2 to the power 4, then what do we get? 8 plus 16, 24 plus 2, that is 28, right? Or 26. 8 plus 16, 24 plus 2, 26. 26. So this indicates that my property, if I denote them by property 1, 2, 3, 4 and 5, I can say only property 2, property 4 and property 5 is present. This is important to me. When I am interested in which properties or which elements are present, but I am not interested in which order they are present, or whether they have any additional characteristics or not, what is their frequency. I am not worried about those things. I know the presence of the element is the only thing that matters. And how many combinations are there? I know that there are 2 to the power 5 combinations of these elements. I know this, that using 5 elements, we have 2 to the power 5 different combinations. Whether to take them, whether not to take them, this. So yeah, all possible subsets of 1. Okay, what is bit masking? I'm coming to it. Bit masking is basically saying that in order to represent 5 elements, whether they're present or not, suppose you can say 10101, this represents that the first element, third element and fifth element is present. So using these bits, when you show this, that which elements are present and which elements are not present, this is a bit mask. So this is a bit mask which says that using 5 bits, out of which these 3 are set bits and the rest are unset bits, what you are saying is that these 3 properties are holding true. The first property, the third property and the fifth property. So this is a particular bit mask. You can say that using this particular bit mask 000100, what you are saying is this is another bit mask which says that the second property and third property are holding, or maybe the second element and third element are present. Okay, so what can we say? For all the 5 elements, being present is totally their choice and they are independent of other elements, right? So whether this second element will be present or not does not depend on whether the other elements are going to be present or not. This is the first idea that we get. So what does this mean? All are independent, and if you recall your class 12 probability, what is the total number of possibilities of all these numbers to be present and not present, and some present and some are not present? What are the total number of possibilities? It is 2 to the power 5. Because there are 5 elements, so every element has the option of being present or not present. If it is present, we are denoting it by 1. If it is not present, we are denoting it by 0. Make sense? So this is basically bit masking. So this topic is more on how we use both the topics together. But if you are not exactly sure about bit masking, this exactly is bit masking, where we say that if I want to denote that P1 and P5 are only present, no other property is present or no other element is present, only these 2 elements are present, I will say that using this 5-bit structure, make everything else as 0 and denote only these two bits as 1. This uniquely represents this. And how I can store it? I can simply store it by the decimal representation. I can say from this I can directly store this as 2 to the power 4 plus 2 to the power 0, which is 17. So when I store 17, there is a one-to-one relationship between the subset I am trying to mean and the bit mask I am representing. Makes sense? So there is a one-to-one relationship. This is basically the subset, and this is, we can say this is basically the outcome or the bit mask, we can say outcome or the bit mask. So we are basically showing this, that there is a one-to-one mapping between them, or you can say a bijection. So there is a bijection between them. I don't know how to represent it, but anyway, there is basically this kind of a relationship, which is a bijection between them. You remember what a bijection is? So it has to be 1 1 and on 2. I am saying that every bit mask means something to me. Every bit mask means a subset to me, and that is what we are saying. Every bit mask means a subset. Every subset means a particular bit mask. So when I see something like 13 over here, suppose I see 13. 13 actually tells me that 13 in the binary representation, it is nothing but 1101, I guess. This is 13. So I can say what this means is that the first and fourth property are not present, and the second, third and fifth property are present. Hope this makes sense about bit masking. So there are 2-3 things that we covered. One is from 00000 to 11111. So this indicates that nothing is present. This indicates that everything is present. How many possibilities are we visiting? 2 to the power 5 in total. We say that this is nothing but decimal 0 and this is nothing but decimal 31 or 2 to the power 5. So using all the values, yeah. Let me see the question. Sir, is it possible we can get multiple subset of one outcome? Multiple subset of one outcome means for a certain subset we'll have multiple outcomes? No, that is not possible. So a particular subset means a certain thing to me. If I say that Pi1, Pi2, Pi3, these are present, I have to say that in the entire bit mask, only this I1, I2 and I3 positions should be marked with 1. Rest should be 0. So a particular bit mask means only one particular subset to me. Many to one. Many to one means, okay, multiple subsets mean an outcome. Not in terms of bit mask. A bit mask uniquely represents a particular subset. You cannot have two bit masks which will say we represent the same thing. Why? Because a bit mask directly tells you when you store any value, any decimal value, it has got exactly one binary equivalent. A binary equivalent will tell you which positions are 1, which positions are 0. So from there you can directly say that whatever are 1, you can, just a second. Any problems? We can try and bitmask. Can you suggest some basic bitmasking problems? Bitmasking problems, every time like in common contests it is a part of. It depends on which, like there are easy bitmasking problems you can always look for. You can search them on CodeChef and Codeforces. You can start with the easy ones. The tougher ones are these topics which deal with bitmasking. So I'll address the first one. Okay, it's clear. Thanks for that. Any other doubt till now? We are going to see it in more detail in the problem that we solve now. Okay. In the problem that we'll be solving, we'll be seeing it more clearly, but the basic bitmask idea is this. Got it. Okay. Let us then proceed and let us analyze a problem. This problem is a very common popular problem and a very big research problem. Hamiltonian path. Hamiltonian path in a graph. So in any graph, which is basically a combination of nodes and vertices, Hamiltonian path is something where we say that there is a path which starts at one vertex and which covers all the other vertices without repeating any vertex and looking somewhat like this. So it will start at one vertex, cover all the vertices, and it will not repeat any vertex. Okay, this is a Hamiltonian path. Why it is important? Because it is NP complete. So it can start over here also, it can start over here also, it can start anywhere. It might happen that there is a Hamiltonian path possible which starts from this but not from this. It is possible that it starts from only a particular vertex. Why? Suppose the graph looks like this. Suppose you have a graph which looks like this. You have something like this. Yeah. So you can see if you start from here, you basically, if you follow this particular route, you cannot go anywhere else. But if you basically start from here and you say I'll be reaching here, then I'll be coming over here, then I'll be coming over here. So you say that there is a Hamiltonian path possible which starts from 1 and ends over here. This is a Hamiltonian path. However, there is no Hamiltonian path which can start from here. You cannot have any Hamiltonian path because there is no out degree. Out degree is 0 from there, right? Yeah. Make sense? Yeah. So now whether a Hamiltonian path is present or not, this is a central question. That is a Hamiltonian path present? Is a Ham path present in a graph? This is a central question which is known as, or which falls under the category of NP complete. If we didn't connect single node from n nodes, then this is Hamiltonian in this case. If we didn't connect single node from n nodes. From n nodes we are... I'm sorry, I didn't get it. I didn't actually get it. Single nodes, n nodes. So there is a bit of lag, but you can tell me clearly what you mean. So the problem is that the thing that I'm mentioning is, suppose this is the only graph which is given to you, and you can have some other edges, but this is one Hamiltonian path which is possible. But if you say I'll search in this manner, I'll start from here and I'll see how I can reach over here, from here how I can reach over here, and so on. N equal to 6, we connect only 5. N equal to 6, 1, 2, 3, 4, 5, 6. Okay, yeah. So we started from here. We say the moment I draw this edge, these two are connected. The moment I draw this edge, this is connected. The moment I draw this edge, this is connected. And so on. The moment I draw this edge, this is connected. And the moment I draw this edge, now the entire thing is connected. So I'm able to form a path from one vertex through all the vertices to a last vertex. And I can say using n-1 edges, which is a good observation. Using n-1 edges, I'm able to connect all the vertices. We know this, that if there is a tree of n vertices, it will have n-1 edges. Make sense? So here also the same thing is happening. This is also a tree which is a very good tree. It is a path and it's a directed path. So we are saying that there is a Hamiltonian path possible. And is a Hamiltonian path present in a graph? This is an NP complete problem, which means it cannot be solved in polynomial time. Okay. Basically, if you can solve Hamiltonian path, you'll be able to solve traveling salesman problem. So TSP in polynomial time reduces to Hamiltonian path. This is basically the problem. So we know that Ham path cannot be polynomial time solvable. Hence, we can only have exponential algorithms to solve Hamiltonian path. That is a Hamiltonian path present. If it is present, it has to give me one Hamiltonian path. There may be multiple Hamiltonian paths present. Okay? Like in a complete graph, there are so many Hamiltonian paths. Like you can choose any direction. You can go anywhere, right? So what can be one approach of finding whether a Ham path is present or not? Ham path basically means this. So what is a Ham path? Ham path basically means this. I'll write it down. A path that visits all vertices of a graph without visiting any vertex twice. Any vertex twice. Okay, this is a Ham path. Makes sense? So we have to find out. See over here, let me give you an example. You have 3. Now suppose it goes something like this and it goes something like this. I'm sorry. Suppose it goes something like this and it can run something like this and it comes something like this. Okay. So now what can you say? You will try starting from here. This will be a first vertex, then this will be a second vertex. If you visit this, you cannot come out of it. But if you visit this, again, in order to come out, you have to revisit this vertex. You have to visit this vertex as the fourth vertex, and through here, you can come and visit this. First this, then this, then again this, and then again this. So in this way, you can cover all the vertices, but this is not allowed. You cannot revisit a vertex. Make sense? You cannot revisit a vertex. That is why this particular ordering is not allowed. So we say that in this graph, Ham path is not possible. In this particular graph, Ham path is not possible. Make sense? Why take any starting vertex? If you take anything other than 1, you cannot reach 1. 1 तक आप reach नहीं कर सकते. You don't know how to reach 1. There is no incoming edge onto 1. And if you start from 1, you definitely have to go to 2. 1 से बस 2 तक ही edge है. And 2 से आप जहाँ भी जाने की कोशिश करेंगे, आप 4 में जाइए या 3 में जाइए, you cannot come back and prevent the revisiting of a vertex. And when you revisit, you are violating the case. So now you need to find out whether a Hamiltonian path exists or not. What can be a trivial way of doing it? Can we say that this Hamiltonian path, any Hamiltonian path is basically a permutation of vertices, which tells us that we are ordering the vertices in a particular manner, vi1, vi2, vi3, and so on up to vin. We are ordering in this manner and we are telling that in this order we will be visiting all the vertices. So this basically represents a permutation to us. A Hamiltonian path basically represents a permutation to us. Make sense? Okay, let me see the idea. Check every node is connected with a single node or not. Every node is connected. You can see over here. Like 1 is only connected to 2. But that is like from here we cannot say whether a Ham path is possible or not. Because just if this is possible, if this exists, then a Ham path would be possible, right? If this exists, then a Ham path would be possible. If we say that this edge exists, then a Ham path would have been possible. 1, 3, 2, 4. 1, 3, 2, 2, 4 would be possible in this case. If we have this edge, then 1, 2, 3, 4 will be possible. So right, just from one edge or 2 edge, we cannot prove this. So over here you see 4 already has got an incoming edge. If you have another incoming edge, we are going to get a Ham path. If you don't have this incoming edge, we are not going to have the Ham path, right? So ultimately what matters is something like this. Tell me if you have got any doubt. That a Ham path basically has a bijection with a permutation. A Ham path says that it is a permutation of vertices which specifies the order in which they are going to be visited. Let me check the question. If any node has 2 vertices, then that should not be Hamiltonian. If any node has 2 vertices, means? Node has 2 vertices means maybe some typo, because a node is the same as a vertex. So all of these basically represents node or vertex. So do you mean that if a node has incoming edges from 2 vertices, or if it has outgoing edge to 2 vertices? What are you trying to mean over here? But no, actually no such property. Like superficially I can say there is no such property which you can directly say. Node has 2 paths. So if a node has 2 vertices, no, like over here what can you say? Suppose these are 4 vertices. From this you have got 2 paths. From here you have got 2 paths. From here you have got something like this and something like this. What can you say? That I'll be choosing this one. I'll be choosing this one to reach the from the first vertex to the second vertex. I'll be choosing I drew it wrongly. Node has two outgoing paths. Okay. Something like this. Suppose all of them have two outgoing paths, so they will look something like this. The first one goes to second and third. The second one goes to third and fourth. Third and fourth. The third one goes to fourth and suppose something at the beginning. This is the case, suppose. So what can we say? We will go from 1 to 2 first. 1 to 2 using this particular edge. Then we'll go from 2 to 3 using this particular edge from here to here. Then we'll go from 3 to 4 using this particular edge. Make sense? So we are having a Hamiltonian path. So no such property actually can suddenly give us the answer, because it's really like dependent on what the rest of the graph looks like. You cannot directly say by looking at only a small part that this will be Hamiltonian or this won't be Hamiltonian. If the idea is that if you can choose certain edges which can help you complete this permutation such that this entire permutation is connected, then you can, okay, by considering every node as starting node and traveling exactly, very good. By considering every node as starting node and traveling each and every starting node individually and traversing with a visited Boolean count, it will take lots of time and it's a naive approach. Very good. So just a different way of looking into it is, if you think about it, what are the paths possible in a graph? Then I want to again come back to this thing and tell me if it is clear to you, or I need to mention again. Please get this well absorbed, that every path is actually a permutation for us. Okay? It is a permutation. It has to start from a certain vertex. Suppose you have only 3 vertices, 1, 2 and 3. So what are the different paths possible? I can say from 1 to 2 to 3. I can go from 1 to 3 to 2. I can go from 2 to 3 to 1. I can go from 2 to 1 to 3. I can go from 3 to 1 to 2. And I can go from 3 to 2 to 1. Makes sense? So all these graphs are permutations. All these basically paths are nothing but the permutations of 1, 2 and 3. What I need to see is if any of this is possible. If any of this is possible, any of these paths is possible, then I know I am done. Right? If any of these paths is possible, then I know that I have got my answer. Does it make sense? Let us suppose that I have got a graph. Suppose in this kind of a graph, if you think about it, what can I say? That 1, 2, 3 for this particular permutation is possible to draw. Yeah. So they are right. There are, if we have n vertices, then there are n factorial possible paths. Possible paths. They may not be like, they may not exist in our answer. They may not be called Hamiltonian paths. If you see that from 2 to 1, suppose you have your graph something like this where 2 and 3 are not connected in this manner. Suppose you have something like this, 2, 3, 1. Suppose 2 is connected to 1, 3 is connected to 1, but 2 is not connected to 3, so you cannot have this path. Okay? So whether any path exists or not depends on whether all these edges are defined. If both the edges are defined, I can say this path also makes sense to me. If both these edges are defined, then this path makes sense to me. Is this idea clear? So can I say I already know the permutations, I know what can be the possible answers, I know Hamiltonian path must be one of these things, but in order to confirm whether a particular path is a Hamiltonian path or not, I need to check that permutation. I need to check that permutation from left to right, whether every, suppose this is Vi and this is Vi plus 1, I need to check that for all the i's, this edge exists or not. If this edge exists, then fine, go ahead. If it does not exist, stop the work right now. This permutation cannot exist. Makes sense? So in this case, I can say there is no ham path. But suppose you have something like this, where it goes from 2 to 1 and 1 to 3. So I can say this is the only ham path which is possible. Why does this ham path not hold? Because 1 to 2 is not possible, so this ham path does not hold true. 1 to 3 to 2, again 1 to 3 is possible, but 3 to 2 is not possible. I can say this does not hold, so this does not hold. Good. 2 to 3 to 1, again 2 to 3 is not possible, so we cannot have this. 3 to 1 to 2, 3 to 1 is possible, but 1 to 2 is not possible, so I cannot have this. 3 to 2 to 1, 3 to 2 is not possible, so I cannot have this. So in this manner, I can cancel out all the permutations which are not valid for me. Does this make sense? So I can say this is the only permutation that is valid because both these edges are valid. Make sense? So I'm going pretty slowly. Let me know if it makes sense and it is understandable to all of you. Great. Vi plus 1, exactly. Vi plus 1 belongs to E for I belongs to 1 to n minus 1 actually. 1 to n minus 1 you can say. Okay. Because there are basically like, yeah, from Vn minus 1 to Vn. In this permutation, this is the last thing that we need to check. So what he has written is from V1 we are visiting, okay. Why 213 is possible, not others? 213 is possible over here. Look at this graph. So we can say 213 is possible because 221 exists, 221 edge exists, and 123 edge exists. Okay. So this path is possible, but look at the others. I'm taking one example now, okay? The last one. Follow it minutely. So I have 3 to 2 to 1. What happens from 3 to 2? I cannot go because there is no edge from 3 to 2. So I say this path is not possible. This path is not possible. This entire thing. If any of the edges is not possible, I will say this path is not possible. Make sense? Makes sense, Hassan? And Guru, I hope it makes sense. It actually like n minus 1 is going to be the last index of I. This is I plus 1. So I will range from 1 to n minus 1, right? Rest of the notation is good. Okay, we'll move ahead because time is short. Let me know whatever doubts you have. We can have a longer discussion on each of them. Okay, great. So now, what is the time complexity of this approach? The time complexity is there are n factorial permutations, and for checking each of the permutations, what do we need to do? We have to check from this I to I equals to 1 to I equals to n minus 1. We have to check each of these edges whether they exist or not. So checking each of these edges means just like that is an easy operation. You can always store all your edges and you can always check whether that edge is present or not, whatever kind of structure you use. You can always, like using n square storage, you can use it. Using n square like an adjacency matrix kind of a thing, you can directly check whether this edge exists or not. So what can you say? That every step is going to take one step, and the total time to validate one particular permutation or invalidate one particular permutation is order n, because I need to read through all the vertices in that path. So this is going to be order n. This time for each permutation, the time for validating or revalidating. Hence, we know the total time is basically n factorial multiplied by n. Okay? Which is quite large. Can we do something fractionally better? We know it will be exponential in terms of n. It cannot be linear in terms of n because it is NP complete. NP complete deals with such problems. But can we make it, better? So the idea is that for this kind of problems, you cannot apply any shortcuts. You cannot apply any property of graphs. You need to explore all the possibilities. You cannot apply any shortcuts. So we have to think about how we can cover all the possibilities but avoid some repetitions. This is the only thing which we have to ensure, that cover all possibilities. I'm sorry. Possibilities and avoid repetitions. This is the only thing I can do. Okay? And this is precisely the technique that employs DP plus bitmasking. What I'm saying is all the possibilities are important to me. All the permutations are equally important to me, but I need to avoid some repetitions. What are the repetitions? Suppose there is something like this. 1, 2, 2, 2, 3, 2, 4, 2, 5, and then this particular thing is not possible. Okay? I am going from 1 to 5 by visiting all these vertices, and then from 5 I cannot go to 6. So I said this is an invalid path. Will this be possible? 1 to 2 to 4 to 3 to 5 to 6. Will this ever be possible? So I've just interchanged this order over here. Will this ever be possible? No, right? Because this particular edge which is not existing is not existing here as well. So here I cannot have this same edge. I cannot take the same edge. Make sense? Makes sense? Now if I say I'll consider something else. I'll say I'll go from 1 to 3, then to 4, then to 2, then to 5, then to 6. I'll plan this particular permutation. The moment I know that this is not possible, can I say that here also it won't be possible? So regardless of whether this is possible or not, this entire thing is not going to be possible, right? This is not a valid path. If 5 and 6 is not present, if your adjacency list of 5 to 6, this tells me that this is going to be 0, something like this adjacency matrix, then I'm going to say that yeah, this edge is not possible, so all these are equally invalid. So if you pre-compute this permutation once again, this is a waste of time, isn't it? This is a waste of time. But what if I know that 5 to 6 is valid? What can I say at that point of time? If 5 to 6 suppose is valid, what can I say? That this one will only pass? Then I don't need to check for these things. I don't require these things. They will also pass, but I don't require them separately. If 5 to 6 is a valid edge, then all the 3 will pass. If it is not a valid edge, none of them will pass. Make sense? Like, it doesn't matter whether this passes or not. It matters, like, it depends on this middle permutation. But you can say, I know how to reach from 1 to 5 by covering all these vertices. So from 5 to 6, if I can reach, that is the end of the story. How I am reaching from 1 to 5 does not matter. Okay, so the principal observation is how I am reaching from 1 to 5. 1 to 5 does not matter. Does not matter. Why? अल्टीमेटली हम क्या बोल रहे हैं, तीनों में ही सेम ही चीज़ है. 5 से हमें डायरेक्टली 6 में जाना पड़ रहा है. वी डोंट हैव एनी चॉइस ओवर हियर. सो 5 to 6 अगर डायरेक्टली जाना पड़ रहा है तो हम क्या कह सकते हैं? तुम अगर 5 तक पहुंच जाओगे 1 2 3 4 5 कवर करके, इट मीन्स द सेम थिंग टू मी. कवर इट इन एनी मैनर एंड आफ्टर दैट फोकस ऑन द रेस्ट ऑफ द जर्नी. इट मीन्स द सेम थिंग टू मी. दिस इज माई ऑब्जर्वेशन फ्रॉम इट. मेक सेंस? सो मैं कुछ ऐसा कह रहा हूँ कि यहाँ पे 5 से अगर हम बोलेंगे कि 5 तक किसी तरह 1 2 3 4 सबको कवर कर लो 5 के साथ कवर कर लो किसी भी तरीके से. हाउ मेनी पॉसिबिलिटीज आर देयर? अगेन यू हैव 4 फैक्टोरियल. 4 फैक्टोरियल मतलब 5 तो अपना लास्ट में रहेगा, उससे पहले तुम किसी भी ऑर्डर में डाल दो. यू प्लेस इन एनी ऑर्डर, यू हैव 4 फैक्टोरियल परम्यूटेशंस. सो व्हाट कैन वी से? फॉर ऑल द 4 फैक्टोरियल माय चैलेंज इज द सेम थिंग. Can 5 successfully take me to the last level? Here I'm assuming that 5 will take me. I'm assuming that the last node will be 5. For this permutation of 5 factorial using the first 5 vertices, I am telling that this particular vertex is going to be, yeah. So that is the idea. So these are getting wasted. I can say we should, if possible, we should try to ignore this. In other words, the order does not matter to me. The order does not matter to me. If I have something like this, that it is covering all the vertices from 1 to 5, and 5 is the last node, then if 5 can take me to the destination, then that is it. If it can take me to the destination, I can say you can choose any of these 4 factorial paths. Choose any of these 4 factorial and take me to the destination from 5. I don't care about which path you're choosing. It should be valid. There should be one valid path. If you can show me one valid path, I know that you can reach me to the destination. I don't read all your 4 factorial paths. You will give me 4 factorial paths, I will fail in all of them because from 5 I don't know how to correctly reach the destination. It means it's a waste of time, right? So this is the idea that we are saying, that using all possible permutations, this is the only problem that we are creating. We know it is NP hard, but still the idea of repetitions comes from this observation that we are spending unnecessary time on the ordering, but the ordering does not matter. What matters is up to a certain vertex, which may be suppose Vk, what are the vertices this is involving? This tells me that okay, there is a path possible using these vertices which ends in a certain vertex Vk. Okay? It may be possible that these vertices also end on a certain other vertex which is Vi, I will treat both of them with importance. What did I say? That if there are some vertices, 5 vertices suppose, some paths they end in Vk, some paths they end in Vi. I will treat both of them separately because their characteristics are different. It may happen that V1 Vi is not capable of taking me to the destination. Maybe it is not capable of taking me to the destination, but Vk can take me to the destination. So they are different. Here this is important. But how I order these things inside it is not at all important to me. It should be just one valid order. Any valid order. It can be any valid order. Right? So this is actually the idea. Again, in order to find the valid order, what do I need? I need the rest of the vertices to form some kind of ordering, any ordering, and the last vertex should actually have an edge to me. I don't actually care. In order to have this ordering possible, what do I need? That there should be some kind of ordering where the last vertex will have an edge towards Vk. But again, this ordering does not matter to me. It should be one valid ordering. This is the only thing that we are drawing from here. That from the beginning to the end of the problem, the ordering does not matter to me. Hence comes the idea of bitmasking using DP. What we say is that for all the n vertices, we are going to use a bitmask which will have n positions. So it is basically a binary number with n positions, okay? N different positions, and this indicates whether a path is possible or not. This will indicate over here like what vertices I have taken in it. This is a subset of which vertices. So if I say it is something like this 0 0 1 0 0 1 0 0 1 0 0, what I mean is, suppose let us number it in this way, 0 1 2 3 4 5 6 7 8 9 10. So there are 11 vertices in total. What I mean from this is that the second vertex has been taken, the fifth vertex has been taken, and the eighth vertex has been taken. Okay? And we will say for every vertex we will store this bit mask. So we will hold a DP which will say whether this mask is possible ending at a vertex I. So I will say this is true if this subset is possible ending at I, ending at vertex I, ending at I. We will say this is true then, and if it is not following that, then false. So we'll have false otherwise. Okay? So these are the two things that I'll keep in mind. Okay? So what does this indicate? Suppose over here, let us have it over here. Suppose this vertex 0, this vertex 1, this vertex 2. It is going in this manner. So what can I say? That does this mask of 0 1 1 exist that ends at vertex 1? What does this indicate? That does a path exist which will have the vertices at positions 0 and 1, that is these two vertices? Will it have these two vertices such that it ends at 1? We know it is true, right? This is the path. So yes, it exists. I can say that yes, it exists, it is true. But if I ask that, okay, this is in binary form, and what is this value? This is basically dp3. So we will write it as dp3 of 1. Similarly, we will write dp3 of 0. Is this possible? So basically it means that using the same thing, dp3 means again 0 1 1. So the path should include the last two vertices and it has to end in 0. Is that possible from here? No. So we will write false. So this is how we are going to represent it. And we are going to see what is the computation now. So don't worry about what will happen, like how to calculate it. Don't worry about that. We are not worrying about how to calculate it right now. But the thing is, if I have these values, then what can I say? If I have all of these values for all possible masks and all possible positions, I can say what do I need? I need that the total masking, which is 1 1 1 1 1 1 1, something like this, all ones. This indicates that the entire subset is there. What do I need? That for any particular I, this has to be true. True, like there exists an I for which this is true. Then I can say that there is a Hamiltonian path. Make sense? That if all the entire subset of points is covered and DP array, okay, DP array says nothing but if I can cover a certain subset, and if that subset represents a path which ends at I, if it is possible in the graph, then it will be true. Okay, so if suppose the mask contains 1 at these 3 positions, which are position 1, 3 and 5, suppose the rest are all zeros, and I am saying that this is going to be like, I am going to take DP, I am going to represent this by the decimal equivalent, which is nothing but 2 plus 8, which is 10 plus 42. So DP 42 3. The moment I say this, what I mean is that does there exist this particular subset of points, or does there exist a path which contains these vertices such that the path ends at 3? So what are the possibilities? It can be something like this. It can be from 1 to 3 to it can be from 1 to 5 to 3, or it can be from 5 to 1 to 3. If any of these paths are there, then this value will be returning me true. From where 42 came, this is the decimal equivalent of the subset that we have chosen. Okay. So you can see every single path which may be of 1 vertex, 2 vertex, 5 vertices, 0 vertices, n vertices, whatever path you take, you can represent it using a bit mask. You give me a subset of points, I can represent a bit mask. And I can tell you what is important to me. I am saying that for my DP, my state has to be what? It has to be a particular subset and a particular ending point. If I know this, that is sufficient for me. I don't need to know before that last point what else is contained. Yeah, every subset is going to give me a unique value, and not only that, that combination matters to me, what is the last value that matters to me. So hence I'm keeping this last value, okay, ending at I. Now what can I say? That if I know that ending at any vertex, the entire subset is possible to be created, can I say that there is a Ham path? If any of this is true, I can say that there is a Ham path. This symbol is there exists. So there exists I for which that relation holds, okay? And similarly, I can say that if for any of the vertices, or if for none of the vertices Ham path or this particular value is true, if I say that for all possible I this is false, if I say that for all I this is false, then I can say no Ham path exists. If I have the correct values for all of this, can I say this? If I have the correct value, if I somehow derive the correct value according to this formulation, can I say that just this thing is going to give me the answer? I should be, right? How I calculate it is the important thing, but this should happen, right? So it's a simple computation. What I said is, for the entire subset which should contain everything in the path, I am just asking simple question. Try ending it over here. Is it true? True means there has to exist one path including those vertices which ends at I. That's it. So if for any I this holds, then can I say there is a Ham path? Yes, I can say. Suppose there is a Ham path from 4 to 0 to 1 to 3 to 2. I can say that DP of 5, so it will be 31, 2 is going to return me true. I can say this, that there is a Ham path which includes everything. This is the bit mask which represents the entire set. I can say that yes, there is a path which ends at 2. So it will give me true. So I can just say that if any of one of them is true, I can find this Ham path. I hope this makes sense. If you have any questions, you can ask. Okay, so now how to calculate. So the first thing, what can I say? That dp 2 to the power I, what will this particular mask represent? 2 to the power I, can we say it represents that the ith vertex is present, only the ith vertex, and we know there is a path which has only the ith vertex, which ends at I only. So this is going to be true. This can be a kind of base case for me. Does it make sense? That this is always going to hold a path that includes that has this kind of masking. What does this masking say? That only one bit is 1. So this is the actually decimal equivalent of, so this is the binary equivalent of 2 to the power I. What can I say? This represents that only the ith bit or ith vertex is present in the path. So I can say, yeah, this is going to be true. This path is possible if it ends in I. Makes sense? So this is going to be my initial case. Now what can I say? I can say, I can start from everything else. I can say that for all dpij or dpji, whatever you say, this is going to be false. I'll start from this. I will say that none of the paths are possible. I'll gradually include them. And this is where I start from. That if a path includes only one vertex, then that has to end at that particular vertex. So for that particular case, I'm saying that it is true. Okay? What next? Now the interesting part is, how can I say that there is a subset of vertices which ends at, suppose, 5. There is a subset with 1, 0, 2, 4. Suppose this is the subset. How can I say that there is a subset which are connected by a path and which somehow ends in 5? It can be anything. I can represent it in this manner. I will represent the mask such that all these positions are set. All these positions are set. So if you have the first position set, which is 0, then for 1 it is set, for 2 it is set, for 3 it is not set, for 4 it is set, for 5 it is going to be set, then you are going to have zeros for the rest. Okay, so I can say this is going to be my mask. This is basically in binary, my mask. I can say this is nothing but, we can calculate it just by, I think, 1 plus 2 3 plus 4 7 plus 16 23 plus 32 55. So dp 55, and it has to end in 5. I know this. So this particular occurrence I can represent in this manner, dp 55 5. This will actually tell me all the possibilities, whether it is possible to have a path with these vertices 1 0 2 4 5 which will end in 5. This will tell me whether it is true or false. How to find it? We can say for this, there are, we know we have to add this 5. So what I look for, that in the previous subset, which is nothing but 1 0 1 1 1, this particular thing, which is nothing but 23, I guess, is 23. So is 23 possible which ends in 4 and 4 is connected? So there can be these possibilities. Suppose this is subset S dash. So S dash will be over here. It is possible that inside S dash there are certain things which are connected to 4 and 4 is connected to 5. Or it is possible that you have S dash over here where the other things are connected, they are connected to 0 and 0 is connected to 5. Either of this has to hold. Or this will be for 1 has to hold with 5 and 1 has to be remain connected with all these things. Or I can say this has to hold for the other thing, which is 2. Makes sense? 2 has to remain connected to 5 and 2 should be connected backwards with these things. These are the 4 possibilities. Can I say that 5 will be connected and 5 will be the ending vertex अगर 5 के पीछे कोई है जिससे वो connected रहेगा? हाँ, is there any node connecting to 5 and up to that node is the rest of the subset able to form a path? वहां तक क्या बाकी जो nodes पड़े हैं 5 के पीछे वो क्या path form कर सकते हैं which can end at 4 or end at 0 or end at 1? जिसमें end कर रहे हैं वहां से क्या एक edge possible है मेरे पास आते हुए? If these two things are holding together, that there is a path which ends at a certain vertex and there is an edge which connects me to that vertex in this order, that it comes from that vertex to myself, I can say that yes, there is a path which is possible which ends at myself and which covers all these vertices. So this is actually the idea. और ये एंडिंग वर्टेक्स किस में हो सकते हैं? ये जो हम मास्क किए हैं इनमें से ही हो सकते हैं. ये जो हम इधर मास्क किए हैं 55 के अंदर यही हो सकते हैं इनमें से कोई एक. इसमें से लाइक ये तो 5 खुद ही है, तो हम कह सकते हैं ये हो सकता है, इसका 5 से पहले ये हो सकता है, ये हो सकता है, या फिर ये हो सकता है. What are these vertices? One among 1024. Make sense? Make sense? So we can say that basically अगर हम 55 से 2 to the power 5 जो कि करंट नोड का आइडेंटिटी है, 5 के लिए बिट मास्क में क्या ऐड होता है 2 to the power 5. अगर हम 2 to the power 5 विच इज 32 इसको जोर कर दे तो ये वाला बिट हट जाएगा. एंड फ्रॉम हियर वी कैन से दैट इससे क्या रिप्रेजेंट होगा, बाकियों के सबसेट. इससे बाकियों के सबसेट रिप्रेजेंट हो जाएंगे, ये वाला सबसेट रिप्रेजेंट हो जाएगा. इस वाली चीज से मैं यही पूछूंगा कि क्या is there a subset that ends at vertex 0 and or is there a vertex which like it ends at suppose it is ending at 0 and is there an edge from 0 to 5. If both of these things hold I can say that ठीक है path possible है. और दूसरे क्या possibilities है, दूसरे कुछ ऐसे possibilities है दूसरे कुछ ऐसे possibilities है कि I can say that DP of 55 और 32 ये अगर हमारा 1 में एंड हुआ और 1 से अपना ये बंदा कनेक्टेड है, 1 से अपना ये बंदा 1 से ये 5 कनेक्टेड है, तो हम कह सकते हैं कि हाँ देन इट इज पॉसिबल. और ऐसे करके हम बाकियों के लिए भी कर सकते हैं फॉर 2 and 4. सो वी कैन से समथिंग लाइक दिस कि जो बिट्स ये रिमेनिंग पार्ट में है, जो बिट्स इस रिमेनिंग पार्ट में उसको अगर हम J से आइडेंटिफाई करें ऑल द पॉसिबिलिटीज, व्हाट वी नीड इज 55 XOR 2 to the power, let us denote this by I. This is I. So we can say XOR 2 to the power I will tell me कि ith vertex को हटा के क्या सबसेट पर आ रहता है, and I will see whether it can end at a certain vertex J. Okay? अगर ये end करता है and there is an edge from J to a single edge, बस एक single edge जो कि J से I तक आता है, I can say that हाँ इससे डायरेक्टली हम बोल सकते हैं अगर ये होल्ड करेगा, अगर ये होल्ड करेगा हम इसे डायरेक्टली बोल सकते हैं कि जो हम चाहते हैं वो भी हम दिखा देंगे. हाँ इससे हम बोल सकते हैं कि दैट मीन्स DP ऑफ 55 I is going to hold. This is going to be true. If any of this, for any I, there exists I for which this is true, I can say that this is going to be true. Makes sense? So this is actually the idea. This is the recurrence. इसको एक एग्जाम्पल से समझते हैं, ठीक है. एक छोटे से एग्जाम्पल से समझ लेते हैं बिफोर वी क्लोज द सेशन. Suppose that there exists a path somewhat like this. Suppose this is the graph. Okay, XOR से क्या होता है, XOR से something like this. Suppose you have this kind of a number. XOR क्या करता है कि जब भी आप ऐसा कुछ नंबर देते हो 1000 जो कि 1 इधर प्रेजेंट है, तो XOR ऑपरेशन क्या करता है, XOR ऑपरेशन 2 1 देखता है तो इसको 0 कर देता है, इस पोजीशन में 0 हो जाएगा. बाकी जो जीरोज है उसके लिए इनिशियल वाला ही रख देगा, इनिशियल वाले में जो वैल्यूज है 0 1 0. तो एक्चुअली बिटवाइज काम करता है. हर एक पोजीशन में क्या करता है कि अगर आपका दोनों ही 0 है तो इसका आंसर में 0 आता है. अगर एक में 1 है, सपोज पहले वाले में एक पोजीशन में 0 है दूसरे में 1 है, तो ये 1 देगा आंसर में. अगर पहले वाले में 0 है दूसरे में पहले वाले में 1 है दूसरे में 0 है तो ये 1 देगा. और अगर दोनों में 1 है तो ये 0 देगा. तो हम कह रहे हैं एक पर्टिकुलर पावर ऑफ 2 यूज करो जिससे कि एक ही बिट सेट हो. उससे क्या हो जाएगा कि हम जबरदस्ती उसको 0 बना देंगे सबसेट में. So from the mask we are removing a bit. This is a technical way of saying it. Okay? From the mask we are removing a particular bit to indicate the subset that remains after removing this vertex from that subset. Make sense? This is the idea. तो यहाँ पे एक एक बिट एक पर्टिकुलर इंपॉर्टेंट चीज कैरी कर रहा है. यहाँ पे बोल रहा है एक एक बिट बोल रहा है कि मैं रिप्रेजेंट कर रहा हूँ ये 2⁻1 वाला कंपोनेंट बोल रहा है कि ये वर्टेक्स 1 प्रेजेंट है, 2⁻3 कंपोनेंट बोल रहा है कि वर्टेक्स 3 प्रेजेंट है, 2⁵ बोल रहा है, 2⁶ बोल रहा है। तो जैसे ही हम बोलेंगे कि हम 2⁻3 वाले कंपोनेंट से जोर करेंगे, ये बोलेगा कि इसको भूल जाओ इस सबसेट से। अब लास्ट जो सबसेट बनेगा वहां से हम क्या करें, बिट मास्क से हम 2⁻3 को हटा रहे हैं, समथिंग लाइक दैट। मतलब वर्टेक्स 3 को हटा रहे हैं जो हम चाह रहे थे। सो नाउ ऐसे हम कह सकते हैं समथिंग लाइक दिस कि अगर ये जो भी अपना वैल्यू है 55 या जो भी अपना अभी का मास्क है, उस मास्क से ऐसा कोई सेट बिट अगर हम हटा दे, ये कहते हुए कि बाकी का, इसको लास्ट वर्टेक्स मान लेते हैं कि लास्ट में आएगा, यहाँ पे कौन कौन आ सकते हैं, ऐसे कुछ जे आ सकते हैं जो कि जे सेट है, इसके अंदर जो भी इसके अंदर सेट होगा ऐसा कोई आ सकता है। तो ऐसे जे के लिए हम देखेंगे कि वेदर J can be present as a ending vertex over there or not, and from J does there exist an edge? Make sense? So I'll quickly cover an example. कोई भी डाउट है तो पूछिए, वरना एक एग्जाम्पल कर लेते हैं समथिंग लाइक दिस, फिर थोड़ा क्लैरिटी मिल जाएगा। This is 0, suppose this is 1, this is 2, and this is 3, this is okay, and we have something like this. Okay, बस हम 4 ही वर्टेक्स यूज कर रहे हैं। सो कितने सारे बिट मास्क है, 2⁴ बिट मास्क है, 0 0 0 0 से लेके 1 1 1 1। दिस रिप्रेजेंट्स कि चारों वर्टेक्स प्रेजेंट है हमारे सेट में। तो अब हम देखते हैं क्या होल्ड करता है। डीपी हम क्या कह सकते हैं, डीपी 0 हम पहले क्या बना देंगे, नॉट डीपी 0, डीपी 1। व्हाट डज दिस इंडिकेट? डीपी 1 हम कह सकते हैं कि दिस मीन्स दैट ओनली द फर्स्ट वर्टेक्स इज प्रेजेंट, 0 0 0 1। आप जब मैं 1 लिखूंगा तब आप बिट मास्क को सोच लीजिए, 0 0 0 1 होगा, इसका मतलब पहला वर्टेक्स प्रेजेंट है। पहला वर्टेक्स मतलब वर्टेक्स 0, दिस इज इंडेक्स 0। सो ओनली एट 0 दिस विल गिव मी ट्रू, फॉर ऑल द अदर केसेस इट इज गोइंग टू गिव मी फॉल्स। फिर हम क्या देखेंगे, 0 से 2 तो इसका ट्रू आ जाएगा, 0 से 2 तो इसका ट्रू आ जाएगा। बट पहले हम देखते हैं समथिंग लाइक दिस कि कैसे हम इसको डिराइव करेंगे। इससे पहले क्या मिलता है कि डीपी ऑफ 1 के लिए क्या होगा, समथिंग लाइक 2, डीपी ऑफ 2 1 इज इक्वल टू 1 इज इक्वल टू ट्रू। ये क्यों है, क्योंकि 2 रिप्रेजेंट्स 0 0 1 0। तो ये बस एक ही सबसेट में एक ही पॉइंट है जो कि 1 है, इसलिए हमने इधर ट्रू बिठाया। सिमिलरली डीपी ऑफ नॉट 3, इट विल बी 4। 4 के अंदर आपका वर्टेक्स 2 रहेगा, देन दिस विल बी ट्रू। और इधर पे डीपी ऑफ 8, इसके अंदर वर्टेक्स 3 रहेगा, देन दिस विल बी ट्रू। मेक सेंस? मेक सेंस? अब देखते हैं कि डीपी 5 पॉसिबल होता है कि नहीं। डीपी 5 क्या कहता है कि आई एम लुकिंग फॉर, या फिर डीपी 3 सोचते हैं, डीपी 3 सोचते हैं पॉसिबल है कि नहीं। डीपी 3 में क्या है, बस ये दोनों प्रेजेंट है और कुछ नहीं। इन दोनों के लिए मैं क्या कहूँगा, इन दोनों के लिए मैं बस यही कहूँगा कि देख लो कि 0 इसमें लास्ट वर्टेक्स रह सकते हैं या फिर 1 लास्ट वर्टेक्स। दीज आर द ओनली 2 थिंग्स दैट मैटर टू मी। डीपी 3 में ओनली 2 वर्टिसेस कैन एक्ट एज एंडिंग वर्टिसेस, आइदर 0 और 1, सो आई ओनली ट्राई विद देम। डीपी 30, इससे मैं क्या देखूंगा, डीपी 30 मेरे पास एक ही पॉसिबिलिटी है कि मैं 0 वाले पोजीशन को यहाँ से हटा दूंगा, इसको मैं जोर करके मैं इसको 0 बना दूंगा, और मैं क्या बताऊंगा कि 0 0 1 0, मैं कुछ ऐसा बोलूंगा कि रिमेनिंग जो 0 0 1 0 है वो क्या तुम 1 पे कनेक्ट 1 पे खत्म कर सकते हो, और क्या 1 मेरे साथ कनेक्टेड है, समथिंग लाइक दिस। कि मैं 0 पे खत्म करना चाहता हूँ। सो व्हाट डू आई वांट टू चेक कि 1 क्या इसमें रहेगा, एंड इफ रहेगा फिर 1 क्या 0 के साथ कनेक्टेड है। जैसे मैं देखूंगा कि 1 0 के साथ कनेक्टेड नहीं है अकॉर्डिंग टू दिस ग्राफ, सो आई कैन डायरेक्टली से दैट दिस इज नॉट पॉसिबल, दिस इज फॉल्स। सिमिलरली मैं कह सकता हूँ कि 3 एंडिंग एट 1 होगा, मतलब 1 को हमें भूलना पड़ेगा, 1 पोजीशन में जो है, इसको अगर हम भूल जाएंगे तो हमारे पास आएगा 0 0 0 1। ये जो चीज़ है, this can end at 0, but can we reach from 0 to 1? We cannot reach. So this will again become false. Make sense? But in the other hand, what will we get? dp5 अगर हम करेंगे, dp5 के लिए can there exist a path which ends at 0? 0 के लिए क्या ज़रूरी है? dp of 5 के अंदर क्या है? Something like this, 1 0 1. So यहाँ पे 0 1 2 और यहाँ पे 0 है 3. This is the bit mask. What can we say? कि अगर हम 0 को एंडिंग पॉइंट लेंगे, हम बाकी के मास्क के बारे में सोचेंगे. So it will give me 0 1 0 0. एक ही बिट सेट है तो उसी के साथ ट्राई करते हैं. वो है 2. Does there exist a path from 2 to 0? 2 to 0 कोई भी पाथ है? नहीं, कोई भी पाथ नहीं है. So I can say this is also false. What if we try the reverse? dp of 5, 1. Sorry, dp of 5, 2. dp of 5, 2 से मैं ये कहूँगा कि 2 को भूल जाओ, rest of the thing उस पर फोकस करो. 0 0 0 1. Can it end at some vertex? Which vertex is it ending in? It can end in only vertex 0. ये vertex 0 पे end हो रहा है. Is it possible कि 0 से मैं 2 को connect कर दूँ? It is possible. So I will say that yeah. Now both the conditions exist. Now both the conditions exist, that this is, first of all, this is true. Why this is true? क्योंकि 0 0 0 1 मैंने इधर देख लिया है कि ये 1 वाला इधर ट्रू है, ये वाला इधर ट्रू है. मैंने ये देख लिया है कि इट इज़ पॉसिबल टू हैव दिस सबसेट विच एंड्स एट 0. मैं जैसे ये देख लिया, फिर मैंने कह दिया कि 0 पे एंड भी पॉसिबल है एंड 0 से हम 2 में आ भी सकते हैं. सो दिस विल बी ट्रू. तो हमें क्या मिल गया कि इस बिट मास्क 5 को हम वर्टेक्स 2 पे एंड करा के प्रूफ, मतलब यहाँ पे दिखा सकते हैं. सो 0 to 2 एग्जिस्ट्स. सिमिलरली हम क्या बोल सकते हैं, अगर हमें 0 to 1 को कवर करना है, विच मीन्स 2 plus 2 square plus 2 to the power 0 plus 7. So dp of 7 इसको रिप्रेजेंट करेगा कि सारे यहाँ पे स्टोर्ड हैं. dp of 7 के लिए आप सारे पॉसिबिलिटीज ट्राई कर सकते हो. आप देखोगे कि 0 को आप अगर रिप्रेजेंट करेंगे फिर आपको कुछ मिलेगा ही नहीं, क्योंकि कोई भी 0 तक आ नहीं रहा है. सो दिस इज नॉट पॉसिबल, दिस इज फॉल्स. dp of 7 to 1 ये आपका ट्रू देगा. क्यों? क्योंकि हम देखेंगे कि dp ऑफ इस 1 को अगर आप हटा देंगे वहाँ से जोर करके, तो बाकी जो चीज़ें हैं वो यहाँ पे क्या है, 2 to the power 0 plus 2 to the power 2 which is 5. 5 ending at 2 वो आपको इधर ट्रू मिल चुका है. So using this you can say that okay it is ending at 2 and from 2 I have an edge which comes to 1. So इसलिए आप कह सकते हैं कि ये ट्रू है, कि 2 से 1 यहाँ पे एज आ रहा है, यहाँ पे डायरेक्टली आ सकता है. मेक सेंस? ऐसे आप सिमिलरली कह सकते हैं dp 7 2 आपका पॉसिबल नहीं. यू कैन प्ले अराउंड विद दिस. ये फॉल्स है. बट हमारे लिए ये तो ज़रूरी नहीं, हमें ये वाला पाथ चाहिए, तो ये भी हमें मिल जाएगा. कैसे? हम इधर पे निकाल सकते हैं कि dp जिसमें 0 2 3 रहेगा वो कौन सा होगा. 0 2 3 अगर रहेगा तो वो होगा 0 2 to the power 0 plus 2 to the power 2 plus 2 to the power 3 which is 4 plus 8 12 plus 1 13. So dp 13, does it end at 0? It cannot end at 0. Can it end at 3? We will say that yes, it can end at 3. ये क्यों होगा? क्योंकि ये 3 को हटाएगा, पहले इसको हटाएगा. 13 है या कुछ और है? 1 plus 4 plus 8, हाँ 13 है. तो ये बोलेगा कि हाँ 8 को हटाओ पहले. जब ये 8 को हटाएगा तो हमारे पास 5 बचा हुआ रहेगा. ये बोलेगा कि 5 एंडिंग एट एनी ऑफ दिस 2 वर्टिसेस 0 और 2, इज इट पॉसिबल? ये बोलेगा हाँ 5 to 2 पॉसिबल है. और 5 to 2 जब पॉसिबल है, मैं कह सकता हूँ क्या 5 to 2 भी पॉसिबल है और 2 से हम 3 में भी आ सकते हैं. देयर आर 2 थिंग्स दैट आर चेक्ड, दैट दिस इज ट्रू एंड देन वी कैन रीच फ्रॉम 2 to 3. So using these 2 things you can say that this is going to be possible, true. And once you know this is possible, अब rest of the thing क्या है? अब निकालना है dp of 0 2 3 1 सबके लिए which is 15. So dp of 15 कहाँ पे एंड कर सकते हैं? हम जब 1 के लिए चेक करेंगे we will use this value कि dp of 13 3, 13 कैसे आएगा? जोर करके 15 जोर 2 to the power 1, ये करके 13 आ जाएगा. Does 13 end at 3? Yes. Does there exist an edge from 3 to 1? Yes. So सारे कंडीशन सेटिस्फाई कर रहे, तो ऐसे हमको मिल गया. ओके, मेक सेंस? बहुत फास्ट में गया हूँ, बट मैं शुरुआत में काफ़ी स्लो गया था, तो आई होप कि थोड़ा सा सेंस बना है. If any doubts, you can ask, because I have a class after this on Unacademy platform. From 7:30 I do have a class. So if you have any doubts, you can ask me over here. वरना आप लोग वीडियो वापस देख सकते हैं, देख के आप लोगों को पता चलेगा कैसे हम लोग फॉर्म कर रहे हैं. तो यहाँ पे हमने ऑप्टिमाइज कहाँ पे किया? व्हाट इज द नंबर ऑफ स्टेट्स? नंबर ऑफ स्टेट्स क्या है? दिस विल ओनली वर्क विद एडजेसेंसी. हाँ, एडजेसेंसी मैट्रिक्स, उसके लिए n स्क्वायर चाहिए. नंबर ऑफ स्टेट्स कितना है? नंबर ऑफ स्टेट्स सोचते हैं कितने सारे स्टेट्स हैं. डीपी ऑफ मास्क एंड आई. सो मास्क कितने सारे हो सकते हैं? 2 to the power n. एंड आई कितने सारे हो सकते हैं? एंडिंग वर्टिसेस मैक्सिमम n. ये है नंबर ऑफ स्टेट्स. ठीक है, हर एक स्टेट के लिए आपका कंप्यूटेशन कितना है? आपको उतने सारे उस बिट्स को हटा के सारे जो सेट बिट्स है उसको देखना पड़ता होगा. सो इट इज 2 to the power n मल्टीप्लाइड बाई n. और आपका इनिशियली क्या था परम्यूटेशन से? इट वाज n फैक्टोरियल मल्टीप्लाइड बाई n. तो इससे काफ़ी छोटा होता है ये. दिस इज क्वाइट स्मॉलर. 2 to the power n multiplied by n is quite smaller than n factorial. Much smaller than. So from here we can say that this algorithm is far better. आप अगर सोचेंगे 2 to the power 20, 2 to the power 20 आपका होगा around 10 to the power 6. ठीक है, और आप अगर सोचेंगे 20 फैक्टोरियल वो बहुत ज़्यादा होगा. दिस विल बी ग्रेटर देन 10 to the power 20. बहुत ज़्यादा है. So we are actually improving it. Make sense? और ये अराउंड 10 to the power 20 एटलीस्ट हम कह सकते हैं. So if you have any questions, you can ask me. This is quite an advanced topic, but actually understanding this will help you in many contests. And meanwhile, I'll be shortly telling you, 1-2 मिनट लगेगा, आपको बता रहा हूँ क्या क्या बैचेस ऑफर हो रहे हैं अभी अनअकैडमी में, so that you know what are the things we are offering. So this is one batch that I'm taking. महायोद्धा 2 मंथ का मास्टर कोर्स है, एडवांस प्रोग्रामिंग पे है. then you have एकलव्य 2.0 फॉर बिगिनर्स 8 मंथ्स का. फिर ब्रह्मास्त्र 2.0 जो कॉलेज और ऑफ कैंपस प्लेसमेंट्स पर है. सब 6 जुलाई को स्टार्ट हुए हैं. You get structured learning path, 1 subscription, unlimited access to all batches and courses, successfully contested competitions and all these things. महायोद्धा जो मैं ले रहा हूँ इसमें आपके एडवांस्ड कंसेप्ट से मैथमेटिकल कंसेप्ट, फिर एडवांस डायनामिक प्रोग्रामिंग है, फिर सेगमेंट ट्रीज है, एडवांस कंसेप्ट इन ग्राफ थ्योरी है, मिक्स प्रॉब्लम सॉल्विंग है. देन यू हैव एकलव्य जिसमें आपके बिगिनर लेवल से आपको एडवांस लेवल तक लेके जाते हैं. फर्स्ट यू हैव बिगिनर टॉपिक्स, बिगिनर लेवल, देन यू हैव एडवांस टॉपिक्स लाइक दिस. फिर आता है ब्रह्मास्त्र जिसमें ये देखिए बिट मैनिपुलेशन में बेसिकली ये चीज़ आता है, बट हमने आज डिस्कस किया कम्प्लेक्स कॉम्बिनेशन ऑफ बोथ द टॉपिक्स, डायनामिक प्रोग्रामिंग एंड बिट मास्किंग. सो ये एक थोड़ा कम्प्लेक्स चीज़ था, वेयर वी आर मिक्सिंग 2 थिंग्स. ठीक है, तो ये सब आपके रहते हैं इंटरव्यूज़ में. उनके हिसाब से 22 वीक का एक कोर्स है जो 6 जुलाई से चालू हुआ है, ऐसे चलेंगे. You have this is the old list of educators. So among the basically educators, you have ICPC World Finalists, you have Codeforce Grandmasters, Lambda top-notch companies, and you have live interactive classes, practice relevant problems at Courtship, and doubt support on Discord. These are your educators, and this is the pricing. 1 महीने के लिए 6,000, 12 months के लिए 33,000. नीचे डिस्काउंटेड है, इसके ऊपर और 10% डिस्काउंट मिलेगा on top of this if you use my referral code Saptarshi 172. So you can use it and then you will get 10% off on top of all these. Okay. So देख लीजिए 54% off है, अच्छे डिस्काउंट रेट से. If you are interested, you can definitely give it a try. Okay. So before I close, any questions? I have only 10 to 15 minutes to go before the next session. So any questions? इसको प्रैक्टिस कीजिए, इस पे खुद एनालिसिस कीजिए, खुद सोचिए क्या चीज़ें मैंने कहा. बहुत चीज़ें मैंने कहा है इस सेशन में, तो इट विल बी गुड इफ़ यू कैन स्पेंड सम टाइम इन इट. एटलीस्ट नेक्स्ट 2-3 दिन में थोड़े प्रॉब्लम सा प्रैक्टिस कीजिए. हैमिल्टोनियन पाथ को आप खुद इसको सॉल्व कीजिए. यू विल अंडरस्टैंड दिस. ठीक है, एंड यू विल ऑल्सो गेन सम कॉन्फिडेंस इन इट. इसमें आपको काफ़ी सारे प्रॉब्लम्स मिल जाएंगे. एंड आप कमेंट सेक्शन में बता सकते हैं हाउ यू फेल्ट अबाउट द सेशन एंड व्हाट काइंड ऑफ सेशंस यू विल बी लुकिंग फॉर. आप क्या चेंजेस चाहते हैं, किस टाइप के टॉपिक्स चाहते हैं, यू कैन लेट अस नो दैट. मैं ऐसे कमेंट्स देखता नहीं हूँ, बट आई विल बी इन्फॉर्म्ड अबाउट इट इफ़ आई गेट एनी सिग्निफिकेंट कमेंट. तो हाँ, आप एडकोडर से एक एडुकेशनल एडकोडर डीपी एडुकेशनल डीपी एक कंटेस्ट था, एडुकेशनल डीपी कंटेस्ट. वो थोड़ा हार्ड रहेगा, मुझे मन था वो भी कवर करने का, बट आज थोड़ा बेसिक जाना पड़ा. उसमें ओ नंबर का प्रॉब्लम आई थिंक वो है मैचिंग. अब देख लेना, मैचिंग है शायद नाम, नेम ऑफ द प्रॉब्लम, एंड इट शुड बी ओ. सो वो आप देख लेना. हाँ, ये एड कोडर्स आप कर सकते हैं. बहुत आपको प्रॉब्लम्स मिल जाएंगे. कोडशिफ्ट में जाके आप अगर सर्च करेंगे, यू विल गेट मेनी प्रॉब्लम्स फ्रॉम कोडशिफ्ट एंड कोडशिफ्ट. यू जस्ट हैव टू सर्च bitmasking, you will get many problems. You can just select DP and bitmasking, you will get many problems. बट ईजी प्रॉब्लम्स अगर देखें तो हैमपाथ आप सबमिट कर सकते हैं हैकर अर्थ पे. आई थिंक हैकर अर्थ पे मैंने सबमिट करके ऐसे देखा नहीं है कि वो जज कैसा है या लाइक टेस्टिंग वगैरह, बट यू कैन ट्राई, दे शुड बी फाइन. सब लोग फॉलो करते हैं. हैमपाथ हैम साइकिल आपको TSP पर भी मिलेगा. सो यू कैन प्रैक्टिस फाइंडिंग द मिनिमम लेंथ हैम साइकिल. सो मिनिमम लेंथ हैम साइकिल इज एक्चुअली TSP, ट्रैवलिंग सेल्समैन प्रॉब्लम. सो हैकर अर्थ पे या फिर कहीं और आप देख सकते हैं कि ये पॉसिबल है कि नहीं इसको यूज़ करना. और इससे हार्डर वर्जन्स आपको कंप्यूटर प्रोग्रामिंग की प्रॉब्लम्स मिलेंगे. यू कैन जस्ट गो टू वेबसाइट्स एंड यू कैन सर्च फॉर देम. ओके, you can go to CodeChef and CodeForces and you can just like this, nothing so complex. You just have to go to CodeForces and जहाँ भी ये प्रॉब्लम सेट है आपका. okay, I've been logged out. Add tag, so you have bitmasks and you will have DP. So when you search them both, you are going to get the problems where you have both of them. You can see, you can now solve this in according to your own difficulty levels. आपका बेसिक आई थिंक 1500 से 1900 आप अगर करेंगे तो, या फिर 1800 आप करेंगे तो बेसिक लेवल के प्रॉब्लम्स मिलेंगे एंड यू कैन अकॉर्डिंगली गो ऑन शिफ्टिंग. ओके, आप देख सकते हैं इन सब में उसका यूज़ है. ठीक है, एड कोडर का मैनेज प्रॉब्लम ट्राई करना, क्योंकि ये अच्छा प्रॉब्लम है. ट्राई करना, आपको शायद ऑनलाइन ये सोल्यूशन मिल जाएगा इफ़ यू आर अनेबल टू डू इट. थोड़ा सा कम्प्लेक्स हो सकती है इनिशियली, बट दिस अ गुड प्रॉब्लम. ओके, कूल देन, लेट अस कॉल इट अ डे देन. कोई लास्ट 30 सेकेंड्स का क्वेश्चन है? प्रैक्टिस दिस, ICPC वगैरह में काम आते हैं. सो इफ यू आर लुकिंग फॉरवर्ड टू दोज कंटेस्ट, देन give a good deal of practice into this. Okay, thank you. Then did you do top coder problems? कुछ सॉल्व किए थे बट अभी याद नहीं है, और DP plus bitmask पे वैसे याद नहीं है मुझे, बट yes, I have sometimes practiced. Great. Take care. कुछ फीडबैक हो मुझे पर्सनली भी दे सकते, यहाँ भी दे सकते. It's up to you. I always look forward to feedbacks. So anyway, take care and good luck. Bye.